Look at this problem. Two charges, right? Q1 equal to 8 microcoulombs, Q2 equal to 4 microcoulombs are 3 meters apart. Find a point on the line joining them where the electric field is 0. Okay, means there are two charges Q1, Q2 here, separated by a distance of 3 meters. This is 8 microcoulombs, this is 4 microcoulombs. Find the point where, right, the electric field will become 0 along the line joining them. Along the line joining them means along this line. Along this line, at what point, right, on this line the electric field will become 0. Now we will divide this problem and this line into 3 regions. To the left of Q1, okay, to the right of Q2, and in between Q1 and Q2. Okay, at where, at what point the electric field can become 0. Now we'll see. So I told you, from a point charge, positive charge, this is 8 microcoulombs of positive charge. Okay, electric fields will be away from the positive charge. Means at this point, the electric field due to Q1 will be like this. Okay, whatever is the magnitude at any point depends on the distance 1 by 4 pi epsilon naught, right? 8 microcoulombs by whatever this distance, some distance. Okay, at this point, what is the electric field due to this Q2? The Q2 is also positive charge. So the electric field will be away from this Q2 only. Means at this point, right, due to Q1, electric field E1 will be like this. Due to Q2 also, electric field will be like this. Okay, both electric fields are in the same direction. Okay, so they'll get added up. So whatever may be the distance here, the electric field cannot become 0, right, to the left of Q1. Only at infinity it may become 0. It's a different case. Okay, right? Electric field cannot become 0 to the left of Q1 because both the electric fields are contributing here, okay, in the same direction. Similarly, at this point, field at this point due to Q2 will be away from Q2. It will be like this. Okay, field at this point due to Q1 also will be away from Q1. Means here also both the electric fields E1 and E2 will be pointing in the same direction. So they simply get added up. At no point on this line to the left, to the right of Q2, right, there is no point where you can expect the electric field to become 0. Okay, similarly, you can never expect electric field to become 0 at any point on the left of Q1 also. Okay, so the only possibility is what? In between these points Q1 and Q2, right, Q1 will be exerting at every point on this line. Okay, at every point on this line, electric field due to Q1, E1 will be like this. Okay, right, at every point on this line, the electric field due to Q2 will be in this direction. Means there will be in opposite directions. E1 and E2 is in opposite direction. So if E1 equal to E2, what is E1 at any point? 1 by 4 pi epsilon naught, right? Q1 by whatever the distance R1 square, okay, by Q2 by R2 square. At that some point we can expect the electric field to become 0 when E1 and E2 are equal in magnitude. They are already in opposite directions. If they become equal in magnitude, that depends on the distance of that point from Q1 and Q2. We can expect the electric field to become 0 somewhere in between those two charges. Okay, so how do we proceed for this? Okay, how do we proceed for this? It is like this. Okay, this is Q1, this is Q2, this is 8 microcoulombs, this is 4 microcoulombs. Okay, right, the distance between them is 3 meters. Distance between them is 3 meters. At every point in between these two charges, electric fields due to both charges are in opposite directions. At some point, right, where the magnitude becomes equal, the resultant field will become 0. Okay, now let that point be X, okay, which is at a distance R1 and from this Q1, and it is at a distance R2 from the point Q2, such that R1 plus R2 equal to, right, 3 meters. This distance in a total is nothing but 3 meters. Okay, so what is electric field due to this point? Here electric field EB equal to 0, say, means the magnitudes of the electric field E1 and E2 should be same. Okay, that is, right, what is electric field due to Q1? 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught, Q1 by R1, Q1 by R1 must be equal to 1 by 4 pi epsilon naught, Q2 by R2. Q2 by R2. So 1 by 4 pi epsilon, 1 by 4 pi epsilon get cancelled. Okay, right, now Q1 by R1 is equal to Q2 by R2. What is Q1? 8 microcoulombs. So 8 by R1 equal to Q2 equal to 4 microcoulombs, 4 by R2. That is R1 by R2 equal to, okay, R1 by R2 equal to 2, or R1 equal to 2r2. R1 equal to 2r2. Okay, right? R1 plus R2 equal to 3 meters we have. R1 plus R2 equal to 3 meters. Okay, R1 equal to 2R2 we got. So 2R2 plus R2, that is 3R2 equal to 3 meters. R2 equal to 1 meter. So R2 equal to 1 meters means automatically, okay, R1 will be, this is equal to 1 meter means, right, this will be 2 meters. Means at 2 meters from the first charge or 1 meter away from the second charge, okay, in between on the line in between these two charges, the resultant electric field will become 0. Okay, this is one aspect, one problem, right? A simple problem. Now next we'll go into the how to visualize this electric field. I told you, right, a charge produces something known as an electric field in the region around it. I told, okay, how to visualize that electric field. Okay, scientist called Michael Faraday, the scientist called Michael Faraday has given a very useful concept of visualizing electric field. Okay, he said that visualize electric field or try to understand, imagine electric field in the form of lines of force. He said field lines, electric field lines. Okay, imagine the lines are emanating from a point charge. If it's a positive charge, we will imagine that lines are coming out of that point charge. Okay, positive charge. If the charge is a negative charge, you will imagine all the lines, electric field lines are, right, going into or converge into that negative charge. Means due to a positive charge, we can visualize, right, the electric field lines to be like this. Okay, radially outward like this. Okay, due to a positive charge. Okay, they will be radially outward like this everywhere. Okay, right? If it is a negative charge, the electric field lines will be radially inward everywhere. Radially inward everywhere. Okay, so electric field lines start from the positive charge, means they are trying to come out of the negative charge, they are diverging from the negative positive charge, they are emanating from the positive charge. Okay, they are going away radially from a negative charge, they are converging towards the negative charge radially into. Okay, this is how we can visualize, and these are called electric field lines, electric lines of force or field lines we can call. Okay, these field lines have some properties. Okay, what are they? It becomes somewhat easier concept. How far it is actually 100% acceptable is a different case. Okay, but it becomes easier if we adopt this Michael Faraday's concept of what you call visualization of an electric field in terms of field lines. Okay, right, now first point is that suppose the electric field line is like this in some region. Electric field line is going like this. Okay, that at this point, what is the electric field? Tangent drawn to that electric field line, right, will give you the direction of the electric field. Direction of the electric field means direction of the electric field is the direction in which a positive charge carrier moves freely. Means if you put a positive charge here, the direction in which it moves is the direction of the electric field. Okay, that is obtained by drawing a tangent to that point. What is the electric field at this point? Okay, right, it will be in the direction like this, tangent drawn to. What is the electric field at this point? Draw a tangent like this. Electric field here will be like this. Okay, if there is a line of force, tangent drawn to the line of force will give you direction of the electric field at that point. That is the first point. Okay, when I say the tangent drawn to the field line will give you the direction of the electric field, right, two electric lines of force will never cross each other. We can never expect one line of force like this and another line of force like this. It is impossible. Two lines of force will never intersect or cross each other. Why? At the point of what you call intersection, right, for this line I can draw the tangent this way, for this line I'll draw the tangent this way. Means I can draw two tangents at that point. Means there are two directions to the electric field, which is impossible. If you put a positive charge here, in which direction you should go, right, it cannot, one particle cannot go in two different directions at the same point, isn't it? So this is impossible. So two lines of force will never cross each other. That is the second important point about this field lines. Electric lines of force, they emerge from a positive charge. Okay, right? They end on a negative charge. All electrostatic lines of force always start from a positive charge. They end on a negative charge. Or if a single positive charge is there, electric lines of force will go away from the positive charge. Up to what point they go? They go up to infinity. They go up to infinity. Similarly, if a single negative charge is there, electric lines of force will appear to come from infinity to that charge like this, radially inward like this. Okay, if we have one positive and negative charge, electrostatic lines of force will always start from positive charge and ending on negative charge. Means electric field lines, they always flow from higher potential to lower potential. Okay, electrostatic lines of force, they flow from, always the direction is from higher potential to lower potential, or from positive charge to negative charge, we say. And what is the intensity of the electric field? Though we cannot directly measure the electric field from lines of force, but I can say, right, where is the field higher, where is the field lower, we can tell. If a positive charge is here, okay, electrostatic lines of force will be going like this. Okay, will be going away from this positive charge. Okay, like this, in all directions. Now you take some small region here. Okay, some small area. Two lines of force are passing through. Right? Consider the same area, almost same area here. Okay, if three lines of force are passing through this much area, only one line of force is passing through the same amount of area here. Okay, only one field line is going. Okay, so here the density of field lines is more, here the density of field lines is less. This point is closer to this charge q. Okay, so 1 by 4 pi q by r square. R is small for this area, so electric field is more. R is larger for this area, electric field will be less. Means, right, in another way, wherever the electric lines of force are more in number for a given area or in a given volume, electric field intensity is more. Okay, wherever the electric field, what you call lines of force, are lesser passing through a given area, electric field intensity will be less. Means, if the density of the field lines is more, electric field is more. If the density of the electric field lines is less, electric field intensity is less. Okay, the denser, more the number of lines of force in a given area, the higher the electric field. Lesser number of lines of force, lesser will be the electric field. Density is more, density of field lines is more, electric field intensity is more. Density of field lines is less, electric field intensity is less. Okay, right? Means, suppose say the field is like this in some region, the electric field is like this. Electric field is like this. What is the electric field at A? What is the electric field at B? How much? Okay, this is B, say. Okay, definitely, right, for in a given area, more number of lines are passing at that point A, and the same area, less number of lines of force are passing at B. So electric field at A is greater than the electric field at B. How much I cannot calculate. Okay, with these lines of force we cannot visualize, but it will give you an idea that here electric field is more, here electric field is less. Intensity is more here, intensity is less here, like that. Okay, that is another property of field lines. Next one, for what you call a line of force is always perpendicular to a conducting surface. Okay, line of force is always perpendicular to a conducting surface. Means it is like this. You take a conductor, some conductor. Okay, it means metal. Electric lines of force, right, they are always perpendicular to the conducting surface. Means electric lines of force will be like this or like this, into the conductor or end on the conductor or start from the conductor like this. They cannot make any angle other than 90 degrees. Okay, electric field lines are always perpendicular to a conducting surface. Okay, whether going away from that conductor or coming towards the conductor, it's a different case. But electric field lines of force, electric field lines are always perpendicular to a conducting surface. They cannot make any other angle. Okay, conductor, later on we'll see, is an equipotential surface. Means electric lines of force will be perpendicular to an equipotential surface also. Suppose what is an equipotential surface will be clear in the next video, right? Suppose an equipotential surface is like this. Everywhere the electric lines of force will be perpendicular like this. At every point on an equipotential surface, electric field lines will be always perpendicular to an equipotential surface. Since a conductor is also an equipotential surface, electric field lines will always be perpendicular to a conducting surface. Okay. Right, now we'll see some field distributions which have come in previous JEE exams or NEET exams. Okay, how questions are coming depending on this field lines. So what are the important points? Okay, now we'll just revise once, right, through problems. Okay, now look at this diagrams. Okay, this is the field line due to a single positive charge Q. Field lines are going out radially outwards. Where do they end? They end only at infinity. If only a single positive charge is there, these field lines will go up to infinity. In some exams, they'll give questions like this also, right? They'll give different patterns. Okay, whether they'll give additionally, they'll add these things also. Okay, a line of force like this. Okay, another line of force like this. Another line of force like this. Another line of force like this. Okay. Electrostatic lines of force, they cannot abruptly end at one point, or they cannot abruptly start midway. Okay, they should always start from the positive charge only. Okay, if it is given like this, it will be correct only. Okay, it will be given like this, it is correct. But if they break the line and give like this, okay, that is not possible. Okay, so this is due to a single positive charge. See, due to a single negative charge, the situation is like this. The situation is like this here. Okay, electric lines of force will be right towards that negative charge, radially inwards, right? They converge on to the negative charge from infinity. Okay, if a diagram is given something like this, okay, lines of force, right? They are abruptly coming from nowhere. Okay, they are ending here. No, it is not possible. Okay, this will be a wrong one. If a particle diagram is given like this, it will be wrong. Okay, due to a single negative charge, lines of force will come from infinity and converge or end on the negative charge. Okay, if two like charges are there, we know that like charges repel each other. Okay, like charges repel each other. Okay, right? Like charges repel each other. Okay, so the electric field lines will get repelled and no two lines of force should intersect each other. Okay, so lines of force will be going away. You can feel the reflection. Okay, lines of force are getting reflected away there because both are positive charges. Same is the case with both negative charges also. Electric lines of force, only thing is direction of arrows will be reverse in this case, but two lines of force, they appear to get repelled. Two negative charges will repel each other, two positive charges will repel each other, but they won't intersect anywhere. They won't intersect anywhere. Okay, if a positive and negative charge is there, okay, placed side by side, okay, so separated by some distance, lines of force will start from the positive charge and end on the negative charge. Lines of force will start from the positive charge and end on the negative charge. Okay, right? And wherever the density is more, the electric field intensity will be more. Wherever the density is less, electric field intensity will be less. For a given area, here we are having more number of lines of force. Here, less number of lines of force. Electric field intensity here will be less. Electric field intensity here will be more. Okay. Now, what happens to unequal positive charges are present? If two unequal positive charges are present, the situation will be like this. Okay, the situation will be like this. This one plus q, this is what you call the lines of force coming from this plus q are more in number. So this has more magnitude, this has less magnitude. Here it has given as plus q and plus 2q here. Here also repulsion is there, but lines will not interact each other. The lines of force, right, they are going away from this. They are getting repelled away from this charge. And these lines of force are getting repelled away from this positive charge. Okay, there you can see the repulsion here. And if there are two unequal opposite charges are present, okay, wherever the bigger charge is there, plus 2q and minus q, see the number of lines of force emanating from the negative charge are less in number, number of lines of force emanating from the positive charge are more in number. That means that positive charge has more magnitude, negative charge has lesser magnitude, but lines of force are going from positive charge to negative charge. positive charge to negative charge. Okay, this is one picture. Second one, now this is another question given. Which of the following pattern of electric field lines are possible? Okay, first one, this is some charge q. Okay, lines of force are going out as we have seen. Okay, they are starting from the positive charge going away. So this one is possible. This one is correct. Okay, now look at this one. This region is a conducting region. Okay, inside a conductor, electric field is 0. Electric field lines also will not be there. We don't draw electric field lines inside a conductor. And I told you, for a conductor, electric field lines always go and touch the conductor normally or perpendicularly. Here, from this charge q, electric lines of force are going away, right, from this positive charge and ending on the one inner surface of the conductor. Inner surface of the conductor, they are ending everywhere normally, you see. Okay, and because it's a conductor, once we enter into conductor, it will be clear. If you put one positive charge q here, negative charge will get induced on the inner surface of the conductor. So, right, the lines of force will start from the positive charge and end on the negative charge and always perpendicular to the conducting surface. From a neutral conductor, if the inner surface has induced negative charge, outer surface will acquire equal amount of positive charge. Means, see here if you place plus q, minus q will come everywhere on the inner surface of the conductor. Okay, from a neutral conductor, if negative charges are coming to the inner surface, equal amount of positive charge will get induced on the outer surface of the conductor. Again, electric lines of force will start from positive charge and start going away. Everywhere, the electrostatic lines of force are perpendicular to the conducting surface. Means, this configuration also is a practically possible configuration. Okay, now look at this one. Okay, right, there is some charge q in a conducting shell. Okay, this is a conducting shell. Here you see at some points electric lines of force are not making 90 degrees, they are making an angle other than 90 degrees. When they are making an angle other than 90 degrees to the inner surface or outer surface, that is not possible, it is impossible. So this is impossible, we say. This type of what you call lines of force are not, electric lines of force are not possible. Okay, now look here. These lines of force are straight. If the electric field is uniform, we will have what you call parallel lines like this. In a uniform electric field, equally spaced lines will be there. Parallel, equally spaced lines will be there. That we call it as a region of constant or uniform electric field. But here you see, as you are going from bottom to top, the number of lines of force per unit area keeps on decreasing. Here there are more number of lines of force. Here there are less number of lines of force. Okay, right? I told you, right? Electric lines of force always start from higher potential to lower potential. Means if you imagine one plane here, this plane becomes an equipotential surface. Okay. Imagine another plane, this plane becomes an equipotential surface. Here potential is more because lines of force are coming here, means this is at higher potential, this is at lower potential. So what is general electric field formula, right? E equal to V by D, or let us call it as VA minus VB by distance between them. VA minus VB by distance between them. Okay, VA minus VB is same for these two planes. Distance is also same, means electric field should be same everywhere here. But lines of force are indicating that electric field is more intense here, less intense here, means this configuration is also not possible. So out of the given 4, only A and B are possible, right? C and D are impossible, we write. Okay, this is another previous year question. Okay, next one. Look at this. This is a previous IIT question. IIT means it has appeared some time back. Okay, Q1, Q2, two charges are there. Lines of force are like this. He is asking 4 questions. Magnitude of Q1 greater than Q2. Magnitude of Q1 less than Q2. At a finite distance to the left of Q1, electric field is 0. At a finite distance to the right of Q2, electric field is 0. Which of these options are correct? It is more than one option correct question it is. Okay, now look at this one. Look at Q1. Q1, some lines of force are coming here. Okay, Q1, some lines of force are coming. Okay, Q2, lines of force are right in the same area. Lesser number of lines of force are coming from Q2. Or lines here we have lesser number of lines of force. Means what? Okay, the intensity of the electric field here is less. Means charge Q2 must be less than charge Q1 because it is what you call surrounded by more lines of force. So the magnitude of Q1 should be greater than Q2. This option is correct. Okay, how do I know that? There are more number of lines of force here. There are less number of lines of force seen here. Simple. Okay, next one. At a finite distance to the left of Q1, the electric field is 0. Means at this point, left of Q1 means at some point like this. Now look here. This is lines of force are coming out of this charge, means what? This charge must be positive. So from a positive charge, electric field always be away from the positive charge, like this. And this is a negative charge. This is a negative charge. Due to a negative charge, electric field will be towards the negative charge. Towards the negative charge, like this. This is due to negative charge, this is due to positive charge. But electric field due to positive charge, which is like this, right? Because the distance from this charge is lesser here, the electric field intensity towards left will be more. Electric field intensity right towards right will be less always, because this distance is more at this point. Okay, electric field intensity rightwards field will be lesser in magnitude than leftwards field. Okay, at any point to the left of Q1, okay, this distance is always more, so intensity of leftward rightward field will be less, intensity of leftward field will be more. Means here there is no question of electric field becoming zero. Okay, at no point we can expect the electric field to become zero. Now look at the fourth option. At a finite distance to the right of Q2, electric field is zero, we are saying. First of all, Q1 is greater than Q2. Okay, now at this point, you see, at this point, okay, distance is less. So what is electric field at this point? Let this distance be R1. Okay, 1 by 4 pi epsilon naught, right? This Q2 by R1. Okay, Q2 is also less, R1 is also less. Okay, but this point, this distance from this point, let us call it as R2. Okay, right? Now R2 is more, right? 1 by 4 pi epsilon Q1 by R2. Okay, R2 is more, Q1 is also more. At this point, there is a chance for the left facing electric field to be equal to the right going electric field due to positive charge. Though the distance is more here, charge is also more here, no? Isn't it? So there is a possibility for, right, E1 due to positive charge, right, and E2 due to negative charge to become equal at some point here. Okay, because positive charge field will be there like this, negative charge field will be like this. Though the distance is more here, Q1 is also more in magnitude, Q1 is greater than Q2, we are saying. Okay, since Q is more, right, there is a chance for E positive and E negative becoming equal somewhere to the right of Q1. So the option is at a finite distance to the right of R2, electric field will become zero. So here the options are A and D. Options are A and D. This is another question, a simple conceptual question. Okay, a conceptual question. Here to the left, charge is less and distance is more. Electric field towards right is always less than the electric field towards left. Here, right, charge is less, but the distance is closer. Okay, here charge is more, charge is higher, distance is also more. Somewhere at some point here, both fields will become equal and opposite. So there is possibilities, right? The fourth option. So A and D are correct. This is how some field related simple questions are coming in many exams like NEET or in IIT JEE mains. Okay, right? Carefully analyze what is given. Okay, wherever field lines are more, field is stronger. Wherever field lines are less, field is weaker. Okay, to the left or towards right, like that you see. Okay, where is the field becoming zero? Okay, right? So we'll see about the electric potential in the next video. Thank you.